Welcome. In this video, we're going to talk through some things with photoelectron spectroscopy, and we are using our kind of models from the POGL that we did in class. So I'm just going to kind of go over some selected questions that I think are important to our understanding. And one of the main ideas behind this POGL was to draw some analogies between the energies inside an atom to something we're more familiar with on a macro scale, thinking about trying to kick a ball out of the ditch. So we started with those examples, looking at a ball in a ditch. And I just wanted to kind of check the analogy here. So the ball would be the thing we're trying to remove from the ditch. That would be like your electron. And the gravity would be the thing attracting the electron to the nucleus. And I saw a lot of people in here wrote proton, but proton's an object. It's not really, an attractive force here. So the force we might want to talk about here is the Coulombic attraction. You can call it the Coulombic attraction or the, electrostatic attraction here. That is what's holding the electron to the proton, is that attraction between there. And then the player's kick, that is your, energy input. And in the example of the, photoelectron spectrum, we're talking about that energy input comes in the form of a photon. That's where energy is coming from. All right, so now we're going to scroll down here. There's some reading about photoelectron spectra, so you want to read through this. And then let's take a look at this lithium atom and see what a photoelectron spectrum would look like for lithium. So some things we should notice about the lithium atom is that you have two electrons that are closer to the nucleus, and you have one electron that is further from the nucleus. And if you think about what we know about Coulomb's law, is that the Coulombic attraction between particles is proportional to the charge divided by the distance. So what that means is if two particles are further away from each other, if the distance is greater, the attractive force is going to be smaller. So that means the one that is further from the nucleus is going to be less attracted. It is going to be easier to remove. So it has a lower ionization energy. So we use IE as the shorthand for the ionization energy. And the ionization energy is analogous to this energy right here. It's the amount of energy required to remove the electron from the atom. It's similar to the amount of energy required to, remove the ball from the ditch. Okay, so the ones further from the nucleus are less attracted to the nucleus, easier to remove. You're going to observe a lower ionization energy. The two electrons that are closer to the nucleus are going to be harder to remove. They will require more energy, so you're going to see a higher ionization energy. And what we see with photoelectron spectra is that we can, shine some photons on our samples and we observe the electrons that get ejected. And what we notice here is this graph that shows us the energy along the x-axis, and then the y-axis is an intensity of the signal here. And this is similar to what we saw in mass spec, where this y-axis basically is telling us the relative number of things at that position. So in this case, what we're looking at is electrons. So when you're looking at the x-axis, what's a little weird about these photoelectron spectra is the energy tends to go in the opposite direction from what we would expect. So usually the 0 is on the left, but a lot of times in these photoelectron spectra, the 0 is on the right. So just really pay close attention to your axes when you're looking at these graphs. That's always a good rule of thumb, but especially with photoelectron spectra, read these axes carefully. And so what you will notice, a connection here between the structure and this graph right here, is that this peak over here looks like it's around 6,000-ish. This peak's maybe around like 500-ish. So this is our higher ionization energy peak. This peak represents a lower ionization energy. Notice how this peak is taller that means there are, and the height of it has to do with how many electrons. So that means there are more electrons at this higher ionization energy peak than over here. And that makes sense. We'd expect this peak to be twice as high as this peak because we've got 2 electrons in this first shell, and we've only got 1 electron in that outer shell. And actually, I mentioned shells. Let's write out the electron configuration for lithium. It is 1s2, 2s1. And then we can actually, should be able to go through and label these peaks. We'll find that each peak corresponds to a position that the electron can have within the atom. So 2 electrons are here in the 1s subshell. That's closer to the nucleus, so it takes more energy to remove those electrons. And then we've got 1 electron over here in the 2s subshell. And again, that's further from the nucleus, so it's going to be easier to remove. It's got a lower ionization energy. So we want to start seeing the connection between this graph and the structure of the atom right here, and think about Coulomb's law and the attraction between these electrons and the nucleus. Let's scroll down and look at a little compare-contrast here. Actually, one quick thing for 27, the takeaway with question 27 is that each peak represents a possible electron location. So notice in here we have, 3 peaks, and that corresponds with the 3 subshells. So another way you can think about a photoelectron spectrum, it's also a piece of evidence that tells us that these shells are actually broken down into subshells. Because we see different peaks, that means there must be 3 different locations where the electrons might exist. In this example, we got some electrons over here in the 1s, some in the 2s, and then some over here in the 2p. The ones in the 1s are hardest to remove because they're closest to the nucleus. 2p are easiest to remove because they're furthest away from the nucleus. Okay, so let's scroll down here, and question 28 is a really good one because it's a compare-contrast one. So the idea here is using this lithium spectra we just looked at as a comparison point, as a starting point. We want to predict what the spectrum for beryllium might look like, okay? So keep in mind with lithium has electron configuration of 1s2, 2s1, and it has 3 protons in its nucleus, okay? Let's look at beryllium. Beryllium is right next to it, so it's got one more electron, so it's 1s2, 2s2, and beryllium has 4 protons in its nucleus. So if we're going to compare and contrast these graphs, what we'll notice, something that'll be similar, is they will both have 2 peaks because they both have 2 locations, 2 subshells. Okay, they both just have a 1s and a 2s. So that's what will be similar. What'll be different is if you look in beryllium, and remember that, the attractive force is proportional to charge divided by distance. The charge of beryllium's nucleus is greater. It's got a +4 charge instead of a +3. So that means its attractive force is going to be greater. So what that means is we say that these peaks are going to be shifted left. So both electrons will be harder to remove than the electrons in lithium. So like if lithium's, let's see, here's lithium's 1s2, 2s1. So if lithium's 1s electrons maybe took 6,000 kilojoules, maybe beryllium's take 8,000. Doesn't really matter what number you pick. It just should be something bigger than lithium's over there. We can't, we're not gonna be able to predict exactly what number. It just should be a bigger number. Okay, and then same thing with the 2s electrons. They're also gonna be a little bit harder to remove. So I'm gonna move them over here a little bit. So the peaks will be shifted left. Other difference will be the peaks will be the same height. And that's because in beryllium, you've got 2 electrons in each subshell, so they're gonna be the same height. In lithium, you had 2 electrons here, but only 1 electron over here. So this peak was shorter. All right, so that's a little bit of analysis of these photoelectron spectra. Actually, let's go down here and look at one more here with kind of sulfur and phosphorus. Notice in sulfur and phosphorus that we both have 1, 2, 3, 4, 5 peaks here. And that corresponds to 5 different locations. And these locations are subshells. And we can actually go through and with using what we know about electron configurations, we can actually label these. So the one with the highest ionization energy is going to be my one closest to the nucleus. That's going to be my 1s. And then my next closest is my 2s. And then I got my 2p. Notice my 2p is taller. That's because there's 6 electrons in it instead of 2. And then what comes next is my 3s. And then my 3p has 3 electrons in it. So notice how it's not as tall as this peak C over here. And then same thing down here with sulfur. So we've got 1s2, 2s2, 2p6, 3s2, 3p4. So you might notice that this one is a little bit taller because it has 4 electrons in it instead of 3. Some other things you should notice is that these peaks over here are all shifted slightly left. So these ones had shifted left, and that's because the phosphorus has 15 protons in its nucleus, whereas sulfur has 16. So the electrons in sulfur are going to be, more attracted to the nucleus because there's more positive charges there. But the one interesting thing in here we want to point out is that this peak, instead of being shifted left, is actually shifted right slightly. And if you're trying to figure out why that is, you can look at the orbital diagram. So over here with phosphorus, with the 3p3, what you have is 1 electron in each orbital. Whereas down here with the sulfur, with the 3p4, notice that, what we have here is we have 2 electrons that are in the same orbital here. So what we have is we have a little bit of electron repulsion happening. Because remember, electrons are negative, like charges repel each other. So the ionization energy over here in sulfur is a little bit less than we would expect, and that's because of this little extra electron repulsion happening here in the sulfur. And we will get more into this when we get into periodic trends, and we'll see there's a couple exceptions there, but this is just a little interesting one to point out, that peak E there. All right, hope this helps. Thanks for watching.